In the dense heart of Omega Centauri, where stars crowd like a bustling metropolis, astronomers have finally located the first of 10,000 missing black holes hidden in plain sight, their gravitational whispers detected by the Hubble and James Webb telescopes working in perfect harmony. For decades, these cosmic giants eluded detection, buried beneath the dazzling chaos of a star cluster so dense it's a gravitational labyrinth. But by combining Hubble's sharp vision with Webb's infrared gaze, scientists pierced the veil of darkness, revealing a black hole so massive it warps spacetime itself. This discovery doesn't just fill a gap in the universe's shadowy roster, it hints at a hidden cosmos of thousands more, waiting to be found. And now, the hunt for the first of 10,000 has just begun. In a stunning breakthrough, astronomers have confirmed the existence of the first of an estimated 10,000 missing black holes hidden within the dense heart of Omega Centauri, one of the Milky Way's most intriguing star clusters. This discovery, made possible by the combined power of the Hubble Space Telescope and the James Webb Space Telescope, has rewritten our understanding of how black holes form and evolve in crowded cosmic environments. But how did scientists find a black hole that had been invisible for decades? Let's break down what this means for astronomy. Omega Centauri is not just any star cluster. It's a massive, ancient collection of millions of stars crammed into a space no larger than our solar system. Located about 15,000 light-years from Earth, it's one of the brightest and most studied objects in the night sky. For decades, astronomers have puzzled over its peculiar behavior. Stars in Omega Centauri move at speeds far greater than expected, and its gravitational pull suggests the presence of something massive, something that doesn't emit light. This led to a long-standing mystery: where are the black holes? Theorists had predicted that Omega Centauri should host thousands of black holes, but when they looked for them using traditional methods, they found none. This discrepancy became known as the missing black hole problem. If black holes were missing, it would mean our understanding of how they form or interact with their surroundings was incomplete. But how could scientists detect something that doesn't shine? The answer lies in the unique capabilities of the Hubble and James Webb telescopes. The Hubble Space Telescope, launched in 1990, has spent decades mapping the movements of stars in Omega Centauri. By tracking the motion of individual stars over time, astronomers can infer the presence of unseen masses. However, Hubble's resolution has limits, especially when dealing with the extreme density of Omega Centauri. Enter James Webb, the most advanced space telescope ever built. With its larger mirror and advanced instruments, Webb can peer deeper into the cluster, capturing details that Hubble could not. Together, these telescopes created a powerful tool for solving the mystery. The key insight came from analyzing the motion of stars near the cluster's center. Black holes, being incredibly dense, exert a strong gravitational pull on nearby stars. If a black hole were present, it would cause surrounding stars to orbit faster than they would if only stars and other normal matter were involved. By comparing the observed motions of stars with computer simulations, scientists identified a star that was moving at an unusually high speed, too fast to be explained by the known mass of the cluster. This suggested the presence of an unseen object with immense gravitational influence. But how did they confirm it was a black hole and not another massive object, like a neutron star or a dense stellar remnant? The answer lies in the mass of the object. Black holes are the only known objects that can exert such a strong gravitational pull without emitting light. By calculating the mass required to produce the observed stellar motions, scientists determined that the object must be at least 10 times the mass of our Sun, a mass range consistent with a black hole. This was the first time such a calculation had been made in Omega Centauri, and the result was striking: the object matched the expected properties of a black hole. This discovery is more than just a triumph for observational astronomy. It provides critical clues about how black holes form in dense environments. For years, scientists have debated whether black holes in globular clusters like Omega Centauri would merge with other stars or remain isolated. The presence of a black hole in this cluster suggests that some black holes can survive in such crowded regions, influencing the dynamics of the cluster over millions of years. This has profound implications for understanding how black holes evolve and how they might contribute to the formation of larger structures in the universe. But why was this black hole so hard to find? The answer lies in the nature of black holes themselves. Unlike stars, which emit light, black holes are invisible. They only reveal their presence through their effects on surrounding matter. In Omega Centauri, the extreme density of stars makes it difficult to distinguish between the gravitational influence of a black hole and that of other massive objects. Additionally, the cluster's chaotic environment, where stars are constantly colliding and interacting, complicates efforts to model its behavior accurately. The combined power of Hubble and Webb allowed scientists to overcome these challenges by providing unprecedented precision in measuring stellar motions and detecting subtle gravitational effects. The discovery also raises new questions. If one black hole has been found, how many more are hiding in Omega Centauri? And what does this mean for other star clusters? Theorists had long suspected that globular clusters like Omega Centauri could host thousands of black holes, but without direct evidence, these ideas remain speculative. Now, with this confirmation, astronomers can begin to map the distribution of black holes within the cluster and study their interactions. This could shed light on how black holes influence the evolution of star clusters and even contribute to the formation of supermassive black holes in galactic centers. Beyond Omega Centauri, this discovery has broader implications for our understanding of black holes in the universe. Black holes are thought to play a key role in shaping galaxies, but their behavior in dense environments like star clusters has been poorly understood. By studying how black holes interact with their surroundings in these clusters, scientists can gain insights into how they grow, merge, and eventually contribute to the formation of larger structures. This work also highlights the importance of multi-telescope collaborations in astronomy. The combination of Hubble's long-term observational data with Webb's cutting-edge imaging capabilities was essential to solving this mystery. For the public, this discovery is a reminder of how much remains to be learned about the universe. Black holes, once thought to be rare and isolated, are now known to be more common and influential than previously believed. The fact that we can now detect them in crowded star clusters opens new avenues for exploration. Future missions, such as the Nancy Grace Roman Space Telescope and the Laser Interferometer Space Antenna, LISA, will build on this work by searching for more black holes and studying their properties in greater detail. Each new discovery brings us closer to understanding the invisible forces that shape the cosmos. In the end, the finding of this single black hole is a milestone. It's not just about confirming the existence of one object, it's about unlocking a new chapter in the story of black holes. By studying how they behave in environments like Omega Centauri, we're gaining a deeper understanding of the universe's most mysterious forces. And as technology continues to advance, we can only imagine what other secrets will be revealed in the vast darkness of space. For decades, astronomers have puzzled over a strange discrepancy in the Omega Centauri star cluster, a dense, ancient globular cluster located about 15,000 light-years from Earth. This cluster, which contains millions of stars, should have hosted a vast number of black holes, yet observations suggested something was missing. Theories pointed to a hidden population of black holes, perhaps billions of them, lurking in the shadows of the cluster's stellar chaos. But how could scientists find these elusive objects? The answer lay in a groundbreaking collaboration between two of humanity's most advanced space telescopes, the Hubble Space Telescope and the James Webb Space Telescope. Together, they uncovered the first of what could be 10,000 missing black holes, revealing a new chapter in the story of cosmic dark matter and the hidden architecture of the universe. The journey began with the Hubble Space Telescope, launched in 1990, which had spent decades peering into the cosmos with its powerful optical instruments. Hubble's ability to capture high-resolution images of distant celestial objects made it an invaluable tool for studying star clusters like Omega Centauri. However, even Hubble's keen eye had its limits. Black holes, by their very nature, are invisible except when their gravitational influence disrupts the motion of nearby stars or when they devour surrounding material, emitting X-rays or other radiation. But in Omega Centauri, the black holes seem to be hiding in plain sight, their absence detected only through the subtle gravitational effects they exerted on the cluster's stars. To solve this mystery, scientists turned to a different kind of telescope, the James Webb Space Telescope, launched in 2021. Webb's primary advantage was its ability to observe in the infrared spectrum, allowing it to peer through cosmic dust and detect faint, cool objects that Hubble could not. However, Webb's infrared capabilities also introduced a challenge: the light from distant stars and objects can be distorted by the telescope's own instruments, requiring meticulous calibration. The team behind the study had to balance these limitations with the potential rewards, knowing that Webb's unique perspective could reveal details about the cluster's structure and dynamics that Hubble alone could not. The collaboration between Hubble and Webb was not just about combining their strengths, it was about solving a puzzle that required both precision and patience. The team began by using Hubble to map the motion of stars within Omega Centauri. By analyzing the velocities of thousands of stars, they could infer the presence of unseen masses, such as black holes. However, the data from Hubble alone was incomplete. The cluster's dense stellar environment meant that some stars were too close to the black holes to be observed clearly, and the gravitational effects of the black holes were often masked by the chaotic motion of other stars. This is where Webb came into play. By observing the cluster in the infrared, Webb could detect the faint glow of stars that had been pulled into the gravitational well of a black hole, or identify the subtle shifts in starlight caused by the black hole's immense gravity. The process of combining data from both telescopes was complex. Each telescope produced vast amounts of information, and the team had to develop algorithms to cross-reference their findings. For example, Hubble's images provided a high-resolution map of the cluster's stellar population, while Webb's infrared data revealed the distribution of cooler, dimmer stars that might be affected by the gravitational pull of hidden black holes. By overlaying these datasets, the team could identify regions where the gravitational effects of unseen masses were most pronounced. These regions became prime candidates for further investigation. One of the key breakthroughs came from the way the team analyzed the motion of stars near the center of Omega Centauri. Black holes, especially massive ones, exert a strong gravitational pull that can cause nearby stars to orbit at extremely high speeds. By tracking the velocities of these stars over time, scientists could estimate the mass of the unseen object they were orbiting. However, this method requires precise measurements and long observation periods. Hubble's long exposure capabilities allowed the team to capture detailed images of the cluster's core, while Webb's infrared sensors provided additional insights into the dynamics of the region. Together, they could measure the subtle wobbles in star motion caused by the gravitational tug of a black hole. The discovery of the first missing black hole was not immediate. It took years of data collection and analysis, with the team refining their models and adjusting for variables such as the cluster's complex gravitational field. The breakthrough came when they identified a region where the gravitational effects were inconsistent with the expected distribution of visible stars. This discrepancy suggested the presence of a massive, unseen object, likely a black hole. To confirm this, the team used a combination of Hubble's optical data and Webb's infrared observations to rule out other possibilities, such as a dense concentration of neutron stars or a cluster of dark matter. The confirmation process was meticulous. The team compared their findings with theoretical models of black hole populations in globular clusters. These models predicted that Omega Centauri should contain a vast number of black holes, but previous observations had failed to detect them. The new data from Hubble and Webb provided the missing piece of the puzzle. The detected black hole matched the expected properties of a stellar mass black hole formed from the collapse of a massive star, and its location aligned with the gravitational anomalies observed in the cluster. This was not just a single discovery, it was the first step in mapping a hidden population of black holes that had eluded astronomers for decades. The significance of this discovery extends beyond Omega Centauri. Globular clusters like this one are thought to be cosmic laboratories for studying the formation and evolution of black holes. By understanding how black holes accumulate in such environments, scientists can gain insights into the life cycles of stars and the role of gravity in shaping the universe. The presence of 10,000 missing black holes in Omega Centauri suggests that these objects are more numerous than previously thought, challenging existing theories about their formation and distribution. This finding also raises new questions about the nature of dark matter, as some researchers have speculated that black holes could contribute to the mysterious, unseen mass that permeates the universe. The collaboration between Hubble and Webb exemplifies the power of modern astronomy to tackle complex, long-standing mysteries. Each telescope brought a unique perspective to the problem, and their combined data allowed scientists to peer into the hidden architecture of the cosmos. The discovery of the first missing black hole in Omega Centauri is a testament to the ingenuity of the research team and the relentless pursuit of knowledge that drives scientific exploration. As the team continues to analyze their data, they may uncover more black holes in Omega Centauri and perhaps even other clusters, shedding light on the vast, unseen universe that lies beyond our current understanding. Black holes are among the most enigmatic and powerful objects in the universe, their existence shaping the evolution of galaxies and influencing the behavior of nearby stars. For decades, astronomers have studied these cosmic giants, yet their true nature and distribution remain a puzzle. Now, a groundbreaking discovery has shed new light on a long-standing mystery: the presence of thousands of missing black holes in a dense star cluster called Omega Centauri. This finding, made possible by the combined power of the Hubble and James Webb space telescopes, is more than just a milestone in observational astronomy. It's a window into the fundamental physics of how black holes form, interact, and shape the cosmos. Let's explore why this discovery matters, what it reveals about the universe, and how it challenges our understanding of these elusive objects. Omega Centauri is one of the most massive and ancient globular clusters in our galaxy, a dense collection of millions of stars crammed into a relatively small space. Such clusters are like miniature universes, where stars orbit each other in a chaotic dance of gravity and motion. But within these crowded environments, black holes, those invisible, gravity-defying monsters, should be abundant. Yet, for years, astronomers have struggled to detect them. The reason? Black holes don't emit light, so they're nearly impossible to see directly. Instead, their presence is inferred through their gravitational effects on surrounding stars or the faint radiation they emit when they devour nearby material. However, in the extreme density of a globular cluster, these signals can be drowned out by the sheer number of stars and other objects. This has led to a paradox. Theoretical models predict that Omega Centauri should host thousands of black holes, yet observations have only revealed a fraction of them. These missing black holes have become a mystery until now. The discovery of the first of these missing black holes in Omega Centauri is a triumph of modern astronomy. By combining the capabilities of the Hubble Space Telescope and the James Webb Space Telescope, scientists have uncovered a black hole that was previously hidden in the cluster's dense stellar environment. Hubble, with its ability to capture detailed visible light images, and Webb, with its advanced infrared sensors, worked in tandem to peer through the dust and stellar debris that had obscured the black hole's signature. This collaboration allowed researchers to detect subtle changes in the motion of nearby stars, which hinted at the presence of an unseen massive object. The black hole's gravitational pull, though invisible, left a detectable fingerprint in the star's orbits, revealing its existence. This breakthrough not only confirms the presence of one missing black hole but also suggests that similar objects may be hiding in plain sight across the universe. But why does finding a single black hole in Omega Centauri matter? The answer lies in the broader implications for our understanding of black hole populations and their role in the cosmos. Globular clusters like Omega Centauri are ancient relics, formed billions of years ago when the universe was young. They are thought to be the remnants of the first galaxies, their stars and black holes locked in a gravitational embrace. Yet, the presence of thousands of black holes in such a cluster challenges existing theories about how these objects form and evolve. Most black holes are believed to form from the collapse of massive stars, but in the extreme conditions of a globular cluster, interactions between stars and black holes can lead to different outcomes. For example, black holes may merge with other black holes or stars, creating intermediate mass black holes or influencing the dynamics of the cluster in ways that are still not fully understood. The discovery of this missing black hole provides a critical piece of evidence to refine these models, helping scientists piece together the life cycles of black holes in dense stellar environments. Moreover, the existence of so many missing black holes in Omega Centauri raises questions about the overall distribution of black holes in the universe. Astronomers have long debated whether the universe contains more black holes than previously thought, and this discovery adds fuel to that discussion. If Omega Centauri alone hosts thousands of black holes, how many more might exist in other clusters and galaxies? The answer could reshape our understanding of the cosmic dark matter problem, as black holes, though not dark matter themselves, can influence the distribution of dark matter through their gravitational effects. Additionally, the study of black holes in dense environments like Omega Centauri could provide insights into the early universe. These clusters are thought to be the remnants of the first galaxies, and their black holes may hold clues about the formation of the first stars and the evolution of galactic structures. By studying these objects, scientists can trace the history of the universe back to its infancy, when the first stars and black holes were born. The methods used to detect this black hole also highlight the power of modern observational astronomy. Traditional techniques for finding black holes rely on detecting their effects on nearby stars or the radiation they emit when they accrete material. However, in the dense and chaotic environment of a globular cluster, these signals can be overwhelming. The combination of Hubble and Webb's capabilities allowed researchers to overcome this challenge. Hubble's high-resolution visible light images provided a detailed map of the cluster's stellar population, while Webb's infrared sensors pierced through the dust and stellar debris to reveal fainter, previously hidden details. This synergy of technologies is a testament to the ingenuity of astronomers, who continue to push the boundaries of what is observable. The discovery also underscores the importance of multi-wavelength observations, where different parts of the electromagnetic spectrum reveal different aspects of the universe. By combining data from multiple telescopes, scientists can build a more complete picture of cosmic phenomena, even when individual instruments have limitations. Beyond their immediate scientific significance, these missing black holes in Omega Centauri have profound implications for our understanding of gravitational physics. Black holes are extreme laboratories for testing the laws of general relativity, as their immense gravity warps spacetime in ways that are difficult to observe elsewhere. The presence of thousands of black holes in a single cluster creates a unique environment where these effects are amplified. For example, the gravitational interactions between black holes and stars in Omega Centauri could generate ripples in spacetime, providing a natural experiment for studying how gravity behaves in extreme conditions. Additionally, the study of these objects could help refine our models of how black holes grow and merge, processes that are thought to be responsible for the formation of supermassive black holes at the centers of galaxies. Understanding these mechanisms is crucial for unraveling the role black holes play in shaping the large-scale structure of the universe. The discovery also has implications for the search for gravitational waves, ripples in spacetime predicted by Einstein's theory of relativity. When black holes merge, they emit gravitational waves that can be detected by observatories like LIGO and Virgo. However, detecting these waves requires precise measurements of the distortions they cause in spacetime. The presence of numerous black holes in Omega Centauri could create a unique environment where such mergers are more likely to occur, providing a new target for gravitational wave astronomy. By studying the dynamics of these clusters, scientists can predict where and how black hole mergers might happen, guiding future observations and experiments. This connection between black holes and globular clusters in gravitational wave detection highlights the interdisciplinary nature of modern astronomy, where discoveries in one field can have far-reaching consequences for others. In addition to their scientific importance, these missing black holes in Omega Centauri offer a glimpse into the complex interplay between stars and dark matter. While dark matter itself remains one of the greatest mysteries of the universe, its gravitational influence can be detected through its effects on visible matter. Black holes, with their immense gravitational pull, can act as tracers for dark matter, helping scientists map its distribution. In dense environments like Omega Centauri, the interplay between black holes and dark matter could be particularly pronounced, offering a unique opportunity to study how these two enigmatic components of the universe interact. This connection underscores the importance of studying black holes not just as isolated objects, but as part of a larger cosmic web where gravity governs the behavior of all matter. The journey to uncover these missing black holes is a reminder of how much we still have to learn about the universe. Despite decades of observation and theoretical modeling, the cosmos continues to surprise us with its complexity. The discovery of this first missing black hole in Omega Centauri is a testament to the resilience and creativity of astronomers, who use the latest technology to probe the unknown. It also highlights the importance of collaboration, as the combined efforts of Hubble and Webb have opened new avenues for exploration. As scientists continue to search for more of these elusive objects, they may uncover even more secrets about the nature of black holes, the structure of galaxies, and the fundamental forces that govern the universe. In doing so, they bring us one step closer to understanding the universe's most mysterious and powerful phenomena. For decades, astronomers have peered into the cosmos, unraveling the secrets of stars, galaxies, and the invisible forces that shape the universe. But among the most elusive mysteries have been black holes, those enigmatic, gravity-defying objects that defy direct observation. Yet, their presence can be inferred through their effects on surrounding matter, and over time, these indirect clues have led to groundbreaking discoveries. The story of black holes is not just about their existence, but about how our understanding of them has evolved, shaped by telescopes, theories, and the relentless pursuit of answers. It begins in the early 20th century, when the foundations of modern astrophysics were laid, and the concept of a black hole was first whispered into scientific discourse. In the 1920s, astronomers like Harlow Shapley began mapping the Milky Way, revealing that our galaxy was far larger than previously imagined. These early efforts to chart the universe's structure set the stage for a deeper inquiry into the forces that govern it. By the 1930s, the idea of a dark star, a hypothetical object with such intense gravity that not even light could escape, was first proposed by physicists like Subrahmanyan Chandrasekhar. Though the term black hole wouldn't be coined until the 1960s, these early theories planted the seeds for a new way of thinking about the universe's most extreme environments. The 1960s marked a turning point. As radio astronomy emerged, astronomers began detecting strange, high-energy sources in the cosmos, objects that emitted vast amounts of radiation but showed no visible light. These were later identified as quasars, and their existence hinted at the presence of supermassive black holes at the centers of distant galaxies. This discovery redefined our understanding of galactic evolution, suggesting that black holes were not just isolated curiosities but central to the life cycles of galaxies themselves. Yet, even as supermassive black holes became a cornerstone of astrophysics, smaller, stellar mass black holes remained elusive. The challenge lay in their invisibility. Unlike quasars, which glow brightly due to the accretion of surrounding matter, stellar mass black holes are often shrouded in darkness, their presence only hinted at by the gravitational influence on nearby stars. It wasn't until the 1970s and 1980s that astronomers began to grasp the scale of the black hole population. Theoretical models suggested that the universe should contain millions of stellar mass black holes, yet observations struggled to confirm their existence. This discrepancy led to the missing black holes hypothesis, a puzzle that would dominate astrophysical research for decades. The key to solving this mystery lay in the study of globular clusters, dense collections of stars that serve as natural laboratories for extreme gravitational interactions. Among these clusters, Omega Centauri stood out. Located about 15,000 light-years from Earth, it is one of the most massive and ancient globular clusters in the Milky Way, containing hundreds of thousands of stars. But something was off. Observations of Omega Centauri revealed an unusual lack of certain types of stars, particularly those that should have formed in the cluster's early history. This anomaly hinted at the presence of unseen masses, objects so dense and massive that they could disrupt the cluster's stellar population. By the 1990s, the Hubble Space Telescope's launch marked a new era in observational astronomy. With its unparalleled clarity and sensitivity, Hubble allowed scientists to peer deeper into the universe than ever before. For the first time, they could study the dynamics of stars within globular clusters in exquisite detail. These observations confirmed that Omega Centauri harbored an unusually high number of massive, dense objects, possibly black holes, whose gravitational influence was subtly altering the motion of surrounding stars. Yet, even with Hubble's capabilities, the true scale of the problem remained unclear. Theoretical models suggested that Omega Centauri could contain thousands of stellar mass black holes, but direct evidence was lacking. The challenge was that these black holes, if present, would be invisible, their presence only detectable through indirect means. This is where the James Webb Space Telescope, JWST, entered the picture. Launched in 2021, JWST represents the culmination of decades of technological advancement, offering a new level of precision and sensitivity. Its infrared capabilities allow it to peer through cosmic dust and detect faint, distant objects that were previously beyond our reach. But the collaboration between Hubble and JWST was not just about technology, it was about combining the strengths of two distinct observational approaches. Hubble's optical and ultraviolet capabilities provided a detailed view of the cluster's stellar population, while JWST's infrared instruments could detect the subtle gravitational effects of unseen masses. Together, they formed a powerful tool for uncovering the hidden architecture of Omega Centauri. The breakthrough came when astronomers analyzed the motion of stars within the cluster, searching for the telltale signs of a massive, unseen object. By measuring the velocities of individual stars and tracking their movements over time, scientists could infer the distribution of mass within the cluster. The results were striking. The data suggested the presence of a vast number of black holes, their gravitational pull subtly disrupting the cluster's equilibrium. But the question remained, how many? The answer lay in the sheer scale of the problem. Earlier estimates had suggested that Omega Centauri could contain up to 10,000 stellar mass black holes, yet none had been directly observed. This discrepancy highlighted the limitations of previous observational techniques, which struggled to detect these elusive objects. The combination of Hubble and JWST's capabilities, however, offered a new path forward. By analyzing the cluster's stellar dynamics with unprecedented precision, astronomers could begin to map the distribution of these missing black holes. The first confirmation came when the team identified a single black hole, its gravitational influence detectable through the way it affected the motion of nearby stars. This discovery was more than just a triumph of observational astronomy, it was a milestone in our understanding of black holes and their role in the universe. But the significance of this finding extends beyond Omega Centauri. The study of missing black holes in globular clusters has long been a puzzle, one that has shaped the way we think about stellar evolution and the formation of massive objects. Theories about how black holes form and evolve have been refined over decades, from the early predictions of stellar collapse to the more nuanced models that account for interactions within dense stellar environments. Omega Centauri, with its unique properties, has always been a key player in these studies. Its age, mass, and density make it an ideal candidate for testing hypotheses about black hole demographics. The discovery of even one missing black hole in this cluster provides critical insights into the processes that govern the formation and distribution of these objects. Moreover, it underscores the importance of long-term observational campaigns. The search for missing black holes has required decades of data collection, analysis, and technological innovation. From the early days of radio astronomy to the precision of modern space telescopes, each step has built upon the last, revealing new layers of complexity in the universe. The collaboration between Hubble and JWST exemplifies this progression, demonstrating how the synergy of different observational tools can unlock previously hidden truths. Yet, the journey to this discovery was not without challenges. The sheer scale of the problem, 10,000 missing black holes, required a level of precision and patience that only the most advanced instruments could provide. The data analysis involved sifting through vast amounts of information, using sophisticated algorithms to detect the faintest signals. Every measurement had to be scrutinized, every assumption tested, because the stakes were high. The implications of this discovery could reshape our understanding of black hole populations across the universe. The findings from Omega Centauri also raise intriguing questions about the broader distribution of black holes in the cosmos. If a single globular cluster can harbor thousands of these objects, what does that mean for the overall population of black holes in the Milky Way and beyond? The answer could have profound implications for our understanding of stellar evolution, galaxy formation, and the role of black holes in shaping the universe. As astronomers continue to refine their models and expand their observations, the study of missing black holes is likely to remain a central focus of research. The discovery of the first of 10,000 missing black holes in Omega Centauri is not just a milestone in its own right, it is a testament to the power of human curiosity and the relentless pursuit of knowledge. It reminds us that the universe is full of mysteries waiting to be uncovered, and that each new discovery brings us one step closer to understanding the cosmos. The journey of discovery is far from over, but with tools like Hubble and JWST, the path forward has never been clearer. The first of 10,000 missing black holes in the Omega Centauri globular cluster has been found thanks to teamwork by the Hubble and James Webb space telescopes. This part of our deep dive into the first of 10,000 missing black holes in the Omega Centauri star cluster has been found by the Hubble and James Webb space telescopes focuses on, explore the open questions, scientific debate, and things that remain genuinely unresolved or mysterious. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The first of 10,000 missing black holes in the Omega Centauri globular cluster has been found thanks to teamwork by the Hubble and James Webb space telescopes. This part of our deep dive into the first of 10,000 missing black holes in the Omega Centauri star cluster has been found by the Hubble and James Webb space telescopes focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, astronomers have puzzled over a cosmic mystery: where did the missing black holes in globular clusters like Omega Centauri go? Now, a breakthrough has finally shed light on this enigma. Using the combined power of the Hubble and James Webb space telescopes, scientists have identified the first of an estimated 10,000 hidden black holes in this ancient star cluster. This discovery isn't just a triumph of technology, it's a revolution in our understanding of how black holes form, evolve, and interact with their surroundings. Omega Centauri, a dense globular cluster located about 15,000 light-years away, has long been a cosmic laboratory for studying stellar dynamics. But its true secrets lay buried in the shadows, until now. The missing black holes, massive, invisible, and elusive, had been theorized to exist for years, yet their absence from observations defied explanation. Some scientists even speculated they might have been ejected from the cluster billions of years ago. But this new finding suggests a different story. The black hole discovered by Hubble and Webb isn't just hiding in the dark, it's actively shaping its environment. By analyzing the motion of stars around it, researchers deduced the presence of a massive, unseen object, its gravitational pull subtly altering the orbits of nearby stars. This black hole, estimated to be several times the mass of our Sun, is likely a remnant of a massive star that collapsed in a supernova explosion. Its detection marks a pivotal moment in astrophysics, proving that these hidden giants are not just missing, they're hiding in plain sight. The collaboration between Hubble and Webb was key. Hubble's decades of archival data provided a long-term view of Omega Centauri's stellar movements, while Webb's advanced infrared sensors pierced through cosmic dust and gas to reveal the black hole's subtle influence. Together, they solved a puzzle that had stumped astronomers for decades. But this discovery is more than just a scientific milestone. It challenges existing theories about black hole demographics. If 10,000 such objects exist in a single cluster, how many more lie hidden in other star systems? How do they form? Do they merge to create even larger black holes, or do they remain isolated? These questions now take center stage. The implications stretch beyond Omega Centauri. By studying these hidden black holes, scientists can refine models of galaxy formation, star evolution, and even the role of dark matter in the universe. This finding also highlights the power of multi-messenger astronomy, the idea that combining different observational tools can unlock secrets beyond our reach. As we peer deeper into the cosmos, the line between the known and the unknown continues to blur. For those who followed this journey, the discovery of this first missing black hole is a reminder of how far we've come and how much further we have to go. If you've enjoyed this deep dive into one of astronomy's greatest mysteries, consider subscribing to FactVerse for daily explorations of the universe's most mind-bending questions. And if you have your own theory about where the remaining 9,999 black holes might be hiding, we'd love to hear your thoughts in the comments. The cosmos is full of surprises, and every question answered only sparks new ones. Stay curious, and keep looking up.